to present our work. You can see our title here, California's Water Future, Predicting Surface Water Supply, especially renewable freshwater resource, and filling in crucial data gaps. Next slide, please. Because we are developing and using our prediction tools to address some of the significant water data challenges, I wanted to start with this quote from Niels Bohr. Prediction is very difficult, especially if it's about the future. Very interestingly, a similar comment we heard while talking with a water manager a couple of months back from California during our first most conversation. So we as a team took this challenge as an opportunity. And we wanted to ask, what all do we need to develop a supply prediction system that is not only helpful to manage the risk of water sectors, but also is usable and dynamic as the factors impacting water resources, they are changing in space and time. Publicly available, data-driven, reproducible, and time and resource efficient. So here we are today. We not only could achieve our first milestone, but also met our mission to foster the use of data science for positive societal outcomes. And here we are going to talk about water. Next slide, please, Kirshna. Okay, so here is our agenda. My team leaders will take the button, as I indicated before. They will come one after another, and I will come back again in the end to conclude. But before we do that, just one point I wanted to mention to you all, that if you are invited to attend our presentation today, you and I, or you and somebody else in this room, we probably have met before. We have common connections. And the connection that comes to my mind, and I'm so happy that Vicky could join us here, it was Bloomberg's Data Science for Society conference back in September 2019, where we were attendees and we met with many team members who are here. Okay, so it's been around 1.5 years, and we are today presenting our product. So having said, please enjoy our presentation, and we will look forward to your feedbacks, advices, and if you have any question along the line, please type on chat box. The next slide, Val, are you ready?
Yes, I am. I was on mute there, of course. But we wanted to start with an overall view of where California is today in terms of its water. So when you hear the word California, it conjures up these images of Hollywood, of this natural beauty, of the fabulous redwoods in the north, the beaches, this easy, this surfer life. And in addition to being the state with the largest population, it's very much an economic juggernaut. And all that economic activity, though, depends hugely on water. Next slide, please. So if we take a closer look at water use, it varies very much across the state. In the northern part of the state, a lot of the water is used to meet environmental needs, which includes water for wild and scenic rivers, for in-stream flow, and for managed wetlands. In the center part of the state, there's more water used for agriculture, basically crop production. And as you move further south, closer to the South Coast, for example, most of that water is used for residential, commercial, and industrial uses. There's also a seasonality to it, in that in wetter years, such as was the case in 2006, much of the water went toward meeting those environmental needs. But in drier years, a lot of the water is moved towards ensuring that farms that the agricultural production and continues across the state. Next slide, please. So what is grown in those agricultural areas? Well, California grows the majority of grapes, pretty much all the walnuts, about like 99% of pistachios. It grows most of the citrus that is for consumption and is pretty much the sole producer for almonds in the United States. And a whopping like 10% of water that is used for agriculture goes towards growing just almonds alone. Next slide, please. In addition to feeding the rest of us, California also needs to feed its own growing population. And the estimate for in 2020, the population is right around 40 million, and that's projected to grow up to about 50 million by the year 2060. And if you look at the image on the right-hand side, most of that growth is going to happen in the central and towards the southern part of the state. Next slide, please. Unfortunately, somebody showed up who wasn't invited to the party, and that is climate change. The state is going through and experiencing these whiplash events where they keep going from a drought to flood to drought cycle. And that has implications, serious implications for the state in terms of meeting its needs. And if we're not hearing about fires, we're hearing about flooding, such as the kind that, that actually caused the Oroville Dam to breach after a mega drought. Next slide, please. So overall, there's a change in seasonality, and this diagram shows the changes in the frequency and timing of seasonal precipitation, but this is across the entire United States. The bubbles indicate the location of the stations where the precipitation was collected, but they also show the sign and the significance of the trend that is occurring. All in all, what we'd like you to take from this diagram is that the wet season is coming later and that the dry season is coming earlier. And this change has implications on the value of water. So next slide, please. What is that value? This is the latest screenshot from the NASDAQ-Veles California Water Index, which was launched in 2018 and represents the current valuation of water as determined by like water entitlement transactions in California in their surface water market. This is again just surface water. So basically what it does is reflect the relative scarcity of water in California. And as you can see, towards the drier months, as we're getting towards the summer, the value of water actually jumps. So California, I'll kind of close this section by saying that California needs a lot of water, and that what it's going to take, because of the changes in seasonality and everything, the reliability of that supply is going to change. Next slide.
Ben?
Yeah, sorry, it took me off guard for lack of cadence reasons, but let me pull up. So just sort of briefly on this mark with the role of the State Water Project. So to summarize this work, this interconnected system from northern to southern California that's over 600 miles long. And to sort of summarize the impact of this is that it reaches over 23 million people in terms of providing drinking water and irrigation water for over 750,000 acres of farmland. Kirshna, or next slide. And so as we sort of continue to focus on the role of the State Water Project, that they're sort of in this interconnected system as we look at service providers, contractors, and water conveyance systems from north to south. Next slide. And then one thing to recognize, especially in the context of this project, that we have reference stations, that is those that have naturally flowing rivers and non-reference stations, so those impacted by human activity. So one of the important aspects of this is that predicting water availability for non-reference stations is very hard, and predicting water availability with these data gaps is also hard, which brings us to the actual project. Next slide.
Okay, I think this is probably where I come in. Okay, hi, I'm Kirshna. So just to go over a little bit of what we've been looking at, the challenge is we understand that the economic importance of water to the economy, to the health, and to the lifestyles of all the people within California. But when we look at what we actually have to sort of evaluate and monitor that volume of water, we really don't have very much. So kind of going back one slide to what Ben was showing, the red dots here are the actual live sensors that are collecting data for water within the state of California, right? And zoomed out at this level, it sort of suggests that there's some reasonable coverage. The black dots are actually the sensors that exist, but they have either really incomplete time series data, or they're not really active, they've been intermittently active. So there's about 84% of the sensors in the state are just intermittent or not active, right? So if you think about it, like all of the crops that we just saw are actually growing in this big dead zone right in the middle. There are entire sections of the state that have no monitoring at all almost. And the sections that do have monitoring are relatively sparsely monitored, or like they're just gaps, very, very large gaps between them. That's kind of the problem. There's a lot of money riding on something that we have very little monitoring of and very little control over. And these things become especially important as, say, the seasonality is changing, as as the water consumption is changing because of those changes in seasonality. Who knows, when everyone goes to the river to get their bucket and they find that they don't have enough. So one of the challenges we took on was well, first of all, most of California is essentially unmonitored. So we have these sensors that are monitoring the rate of stream flow. So the flow of water through these sensors, it happens at some cubic feet per second. And there are about 812 sensors within California. Only 131 of them have reasonably complete data. Going back about 40 years, they collect data every 15 minutes or daily. So what we wanted to do, one of the challenges that we took on was, okay, trying to understand and trying to predict what for the sensors that exist that have good data, can we make forecasts forward for like how much water will be available next year or the year following, right? Because you can't make, for something like that, it's hard to make decisions based upon just 6 months or less of data when you're planning for the future. So you wanted to understand, what the predictions are for the future, as well as the max and the min ranges. Those will have implications for flooding and land use. And also we wanted to fill in the gaps, right? So can we use the information for the sites that we know to figure out what the story is in the sites that we don't know, or we have only partially know, right? That's what we've been trying to really understand. And then the last part is also to visualize the results and make it in some way usable, right? And any feedback that you guys have is always appreciated. So this picture just shows some forecasting that we did for, this is like for missing data. So yes, we can actually reconstruct missing data from sensors that have, incomplete data. What we did is the blue line indicates the actual data. So we have here a sensor that has some partial data. There are some periods of time when it actually had data, and then there's some intermittent gaps here. Sometimes it's a little bit hard to see because the orange line kind of covers those sections where the gaps are. but the orange line represents our predictions for those locations, right? And the fact that they're relatively well covered shows that we can actually, you know, with reasonable accuracy, reconstruct the data for a site with missing data using information from sites that have data. This is an example of forecasting. So we're actually forecasting 1 year out into the future. This is a site located near Alameda Creek in California. Now, again, the blue line shows the actual, the actual data for that year, but based upon, training the model on previous years, we were able to make a forecast or a prediction for this same location. And we get reasonably, we get reasonable prediction. Now the scale of this picture is a little bit tricky, but if you look at this, the average, say the data is in the range of 280 cubic feet per second at these peaks. So we're only missing the peak by about, like 5 or 6 cubic feet per second compared to, so that's actually a pretty reasonable accuracy, given that we've, they'll of course improve as we train the model longer and do some, this is kind of phase 1. So you can see what we've done here is we have reasonable accuracy over the course of a single year. That's actually double the amount of forecast that the Bureau of Natural Resources and stuff use to predict, say, water availability for fires or any of those other types of challenges, right? We basically are able to reconstruct a time series or to forecast forward a time series that's about double of what people are already using. And the last part was just to sort of show you a little demo of what this looks like. We've created, it's like you can only see what you can't see what you can't see, right? The challenge is, how do I make this data visible in a way that users can actually take it and work with it and access it, right? So let me sort of show a little demo of what we have here. Jonathan was very helpful in making this. So if I zoom in here, you can see that these are these are just various sensors around the state. Now, the blue ones, which are really hard to see, are, I think, the ones that are reference. Yeah, they're reference stations versus the red ones are non-reference. Reference meaning that it's a site that's not human impacted as much. So it's much more natural. The flow of the water there is more natural. Whereas the non-reference site is like, if you imagine, the LA River snaking through the city, like there's lots of diversions by the time it gets over there. So that flow is impacted. And in this, we can also include a lot of additional information, like the watershed information, as well as, say, information on the state water project infrastructure, so their routes, power plants, all sorts of other good stuff. But what we've done is allowed us to actually take we can click on these individual sensors now, and then we can we can act, and then we have our models sort of listed here, but we have all of our predictions kind of created here. These are just the first set of models, and you can sort of see, how well the blue line is the actual data, and then all of our models kind of run down the spectrum. And as you zoom in here, as you zoom in, you can see how well we're doing compared to what the true values are. It's very peaky, so it's always hard to pick those peaks. But with reasonable accuracy, we're getting some accurate prediction. And this, the goal is to allow businesses or builders, houses, the governments, local governments of those cities and towns that are in the vicinity of all these sensors, to get a sense of, okay, are you going to have a low flow year? Are you going to have a high flow year? Are you going to should you be more worry about larger flooding or larger drought in your area, right? Will you have to pump water? Will you have to buy water? All those types of questions can we can at least give a better answer to those types of questions. And this shows sort of historical data on stream flow that's there, you know, the actual values versus some of the predicted values. And let me hand it back. Okay.
Thanks, Kirshna. So how are we achieving our goals? Why did we choose river flow versus reservoirs, you know, water storage or groundwater, where kind of 50 to 60% of the water that we are using in California comes from groundwater? It is because water is a circulating resource, okay? If you look at the entire globe, you would see that the storage of water in the rivers, it's about 2,000 cubic kilometer or so per year availability. But we need, our demand, globally speaking, it's around 3,800 cubic kilometer, okay? However, the flow of river, it's in the order of 45,000, okay? So we are not even using 10% of the circulating resource, okay? So this understanding of hydrology, understanding how the society impacts water resources, talking to our users, what do they need? How are they doing? How are they predicting? Okay, what kind of resources are they using? And at the same time, leveraging the amount of data that we are gathering, that we are producing, okay, land-based data or satellite-based data, or to meet the data challenges, we hydrologists and social scientists need help of the data scientists. And then once we have our data products, how do we communicate those outputs back to the society, back to the users? And the users are ranging from the domestic users like us, you know, people who are using water on a daily basis, or maybe the water managers who want to use the outputs from our models for decision making, right? So there comes collaboration. We need to model the dynamical system. It's a coupled human and natural system. So think about the puzzle. River water flow is giving you the best estimate of water availability, right? So we need to predict that. However, we are reshaping our water resources, right? So the puzzle, and how do we solve that puzzle? So we realized that there needs to be a collaboration between the scientists, the natural scientists, the social scientists, the data scientists, and AI modeler, Kirshna, right? Data guys, we have Xiuyang. I'm going to introduce them with you. Ben and Val, and our visualization team, the web development team leader, he couldn't be here. He comes from Brazil. We are leveraging the power of networks and the data science and, you know, the understanding of the social science. And this is our approach. Okay, next slide, please. So we have used a range of data. We have collected a range of data, cleaned them and all, you know, and a range of modeling systems. So, you know, we can talk at length about that, but I'm not just going to do that right now. And I'm going to skip this slide and go to the next one. And here comes the network and the human wealth, as I was talking about. So the approach involves putting together a team, and it all started with data science for social good. Okay, the conference. Vicky is smiling, and it's our pleasure to have Vicky here today. Thank you. So the human wealth, we invested a lot of time to to put together a team that works. Okay, so the collaboration between us, it brought together the pieces of puzzles, okay, that solves not only California's data challenge, the challenge is everywhere, right? So this team worked consistently and effortlessly, you know, on 100% volunteering effort, no funding, no support at all. So we are all volunteers. We meet after 5 o'clock. So you might be wondering, why 5 o'clock? That's the reason, okay, after work. And then the next slide, please, Kirshna. And meet our army. The other half of our human wealth, our students. So all these happy faces, they are our next generation of scientists whom we are training. They come from the academic institutions where we belong, and we are preparing them to take the challenge as leaders as we enter into the newer and second phase of our project. Next, Kirshna. So I just want to leave you with this. What next? So California is not alone, right? So over 2.4 billion people are currently living in highly water-stressed areas. Just take a look at the panel of the figure that we have on the upper left-hand corner. Okay, so all those red dots. And did I mention that we are only using about 10% of renewable freshwater resource? That's correct. The amount of water stored in all these rivers of the world, it's lesser than what we need, but the amount that is flowing, it's 10 times, over 10 times to what we actually need. So then do you see the opportunity? Do you see where we must be investing, how we must be collaborating, how we must be cooperating between countries, between, you know, policymakers, between borders, and, you know, all sorts of things. And my class is now full of people who are interested in investments in water. Okay. So, and the chart that you see on the right-hand side, that's the first most paper that I came up with. It's published in PNAS 2020. It assesses the value of water, okay, as we use water for agriculture. And not to mention, I must mention, 70% of the water we are using all across the globe is for irrigation, okay. So, just to look at the challenges versus opportunity we have, okay, and assessing the value of water, okay, as we clean, as we fill in the data gaps is our next step. And we would love to get your feedbacks. We would love to get your advices to that will help us to do better and maybe find an economist to join our team, helping us doing assessment of water in a better way. Because know that RFWR has never been used to assess the value of water before, and we want to do that. Next slide, please, Kirshna. And before we open our floor for discussions, I would like to acknowledge the help of Paul Alabi from NOAA CESART for helping us to use the computing resources. And then National Science Foundation's RU support for one of our students, Carol, Columbia Data Science Institute support for Jackie, Alejandro, Brandon, and Irene, and NOAA CESART support for Ishrat, Esmeralda, and last but not least, our earlier student, Arzu by Bardi, and Professor Ronak Etematpour for helping us getting USGS stream flow data sets. So with that, I would love to open this floor for discussions. Next slide, please, Kirshna. Thank you.